Okay, in a perfectly inelastic collision, two objects collide and stick together. The way to remember this is inelastic and stick. So inelastic, stick together. Kinetic energy is lost in this type of collision in heat or sound. So I'm going to do a quick example for you in the next slide, but here are some examples you can read. Next slide just gives you an example, so I'll quickly go through it. We have an 1850 kilogram car at rest. So I'm doing its momentum. So mass times velocity plus the momentum for this car going at 22. It's going to stick. So we're going to go 1850 plus 975 because they stick together and we're wondering how fast they go. So this is the example where it's separate and then they stick together, one of those three that I mentioned previously. And you'll find that the instant after they hit, they are going at 7.59 meters per second. Now kinetic energy will be lost. If we look at the kinetic energy before, we see that we're going to use the 1/2 mv squared, and the big truck was at rest. So now we're going to get like 2.36 times 10 to the 5th joules of energy before the collision. After the collision, we're going to see that both of these things are together. They're more massive. So that's the mass together. But now they're going at 7.59. So when I do that, I find that we really only have 8.14 times 10 to the 4th joules of energy. So when I subtract these two, I should get 1.5 times 10 to the 5th joules of energy that is lost. Okay, two objects can be moving. So let's say that we have a giant snake going to the right at 3.5, and we have a little capybara trying to get away from him running at 2.2. So they're both running to the right. Watch those signages. But unfortunately, the capybara grabs him, and the question is the instant after, how fast are they going together? And the instant after he captures them, they're both going at 3.43 meters per second. If you go through and you plug this into 1/2 mv squared plus 1/2 mv squared, find the kinetic energy before, and then go ahead and do 1/2 mv squared here after, you'll find the difference between the two is right around 6 joules of energy that is lost. Okay, for time's sake, I'm going to one and go to elastic collisions. Elastic, they're not deformed, they move away from each other, and no kinetic energy is theoretically lost. Marbles or billiard balls colliding. If you've taken chemistry, we assume the kinetic molecular theory states that molecules hit with no loss of energy. Okay, so again, watch those signage here, but I'm going to take this 0.015 kilogram marble, moving to the right at 0.225 meters per second. I've got this 0.03 kilogram marble moving to the left. Notice I'm putting that negative 0.18 meters per second. Now, they're not going to stick together. After the collision, the smaller one is going to move to the left, and that bigger one made it change its direction. It knocked it to the left. Plus, we have the bigger one, and the question is, well, how fast is it moving? And you might, envisioning this, think that the marble might, either slow down, keep going to the right but slow down, or keep going to the left, sorry, but slow down, or maybe it changes direction, going to the right but, pretty slowly. If you plug the numbers in, you find that it actually does change direction very little bit, 0.09 meters per second. To the right, though, this time, it's positive. If you plug this in, 1/2 mv squared plus 1/2 mv squared before, and then 1/2 mv squared plus 1/2 mv squared after, you find that both sides of the equation, you should get real close to 8.66 times 10 to the negative 4 joules. No kinetic energy is lost. Okay, we're going to do an example of a perpendicular, and those are actually solved differently, so kind of take note of this. I have a little car, a 1,500 kilogram car, traveling at 25, it's traveling faster, 25 meters per second to the west. I have a 10,000 kilogram car, much bigger car, traveling at 15 meters per second, and they're going to collide and probably move off in that direction. I apologize, I'm running out of room here. What I want to do is I want to find the momentum of each car before the collision and make sure that I have it, I hope that works, have it and bring the momentum up. So if I take 10,000 times 15 to get the momentum before, that will be the momentum afterwards. So momentum-wise, I'm going to get 150,000 kilogram meters per second for the bigger car. Okay, so I just moved this vector over here. For the little car, I'm going to go 1,500 times 25. The momentum there is 37,500. And that's the momentum there. Now, what I'm going to do is do the Pythagorean theorem to find the hypotenuse here of the momentums. So if I take 37,500 and 150,000, that's the momentum before and after the crash, because momentum is always conserved. What I'm going to find is, doing the Pythagorean theorem, that the momentum after for both of the cars is going to be 1.55 times 10 to the 5th kilogram meters per second. All right? And then we're going to do a couple of things. This is what direction does it move? We could find the angle here, and we could find the angle here. It doesn't really matter, but you could use that using the tangent of theta. And I think if you use the tangent of theta, you should find this angle right here is 76 degrees. Okay, this one's obviously 90 minus 76. Lastly, though, is you need to find the velocity of the cars at the instant that they crash, right here. They're moving off, and we want to know what's the velocity that they move with. Well, if their momentum is conserved, we know it is. Their momentum, after I do the Pythagorean theorem, is this. Now, just looking at units, if I divide this total momentum by the mass of both of them together, the 10,000 plus the 1,500, I will get, it's supposed to be a 1,500, I will get their velocity that they move off together with, and that is 13.5 meters per second. Okay. Next slide, I don't have a lot of time for this one, but what I basically did here, I break it up into the x and y directions. So if we're not in a nice perpendicular mode, what I do is I say, hey, this is the momentum I start with, and it's only in the x direction. I've got nothing in the y to start with. Afterwards, then, I'm going to take this x direction, and I'm going to say it's conserved. And what I have is I have this one, cosine of 30 times m1v1, and I also have the cosine of 60 times m2v2. And that's what I put together. They're both positive, they're both to the right, and I set them equal. For the y direction, I had nothing to start with, 0. So 0 will be what I continue with. I will have that, which is going to be positive, and that will be the sine of 30 times m1v1, minus that, which is the sine of 60 times m2v2. And set it equal to 0. Now you'll have two equations, and you'll have two variables, and then you have to solve it.